So we're going to go over some probability theory. It's going to be what you need to understand inferential statistics. I'm not going to go into anything beyond that in terms of probability theory. I just want you to have a solid understanding of how probability theory applies to inferential statistics. So when I draw a sample from a population, what's the level? How close does that sample represent the true population mean, for example? So how good an estimate is my sample mean of a population mean? I will also use inferential tests. I'll usually use probability to draw inferences from inferential tests. So I want to draw the conclusion that the results of my study truly represent a difference relative to, say, a treatment or a control group. And I want to be able to draw an inference or draw a conclusion about that. So the example I'm going to use is from the North Bay, Ontario Museum. One of the founding families in North Bay had put together a million jelly bean jar as part of the Great North Bay Expo of 1925. That million jelly beans in a jar was a great tourist attraction during that expo. It was on public display, and people could stare in awe at a million jelly beans, black and white jelly beans. And then after the expo ended, they kept the jelly beans in storage, and it now forms part of the collection at the North Bay Museum. The jelly beans are almost 100 years old, so 95 years old. And they've been kept in perfect condition. So they've been kept in a tightly sealed, massive jar that'll hold a million jelly beans. Proper humidity control, temperature control, and the jelly beans have not been exposed to any direct sunlight. So, and it's now part of the collection, and people, it's a tourist attraction for the city of North Bay. People come to North Bay, visit the museum, and some people will come a long way to visit. It's like the Dion quintuplets, if you know what that is. The jelly beans are something similar to that. But over the years, there's been some contention amongst North Bay residents and local amateur historians. And the contention is that they don't believe the jar has an equal number of black and white jelly beans. So they want me to investigate this issue. So, historically, the rumor or the belief is there's 500,000 white jelly beans and 500,000 black jelly beans. And I'm supposed to run a study to assess if it's true that there are equal number of black and white jelly beans. Now, I thought of this as an MRP or capstone project for RAP students. And I could have put together a team of 5 students on this project. And their job would be to count all of the jelly beans and mark down whether each jelly bean, whether it's black or white. So I'm thinking 5 students, a million jelly beans. I think over one semester they should be able to count 200,000 jelly beans accurately. But then we did an assessment and realized that this just isn't feasible. They didn't want the jar being completely emptied. They didn't want anyone really messing with it because the jelly beans are old, and they don't want them damaged. And it's like they're worried too. It's like you get all those jelly beans, maybe someone might sneak one and eat one or something. So they've left it up to me to basically run the study, and I'm a bit limited in terms of what I can do. So my sample size is 4. I can only sample 4 jelly beans from that jar. I randomly sample. I have museum quality gloves, and they go right up to my elbow. I can reach deep into that jar to grab a jelly bean, and I'm sampling with replacement. So once I pick out a jelly bean, I look at it, mark down its color, and then I put it back into the jar, and then I dig deep into the jar again to pull out a second jelly bean. So I have a sample size of 4. I do that 4 times. Now, and my outcomes, right? I can either, if I pick 4 jelly beans, they could all be white, no black jelly beans. I could pick 1 black, 3 white. I could pick 2 black, 2 white. I could pick 3 black, 1 white. And finally, I can pick 4 black jelly beans and 0 white jelly beans. That's for my 4 picks. And just like we did with the coin toss life event study, and looking at the outcomes for people that end up at a New York City hospital being tested for COVID, here's outcomes for my study. Now, I'm assuming it's a 50-50 proposition here. So I'm assuming that they are correct, that there truly are an equal number of black and white jelly beans. So when I create my little probability distribution, I will create it under the assumption that there truly are an equal number of black and white jelly beans. That's referred to, as we'll get to that after study week, that's referred to as a null hypothesis. The null hypothesis is status quo. The knowledge as we know it is correct. And the knowledge that we know is that's 50-50 based on historical text and documents. Each branch represents an outcome. So here's the first pick. It can be the outcome is either white or black. The second outcome will be white or black. And it'll be a path. Like I could pick for 2 picks, white, 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 black, black, white, and black, black. And then I go up to 3. And here are all the possible outcomes for 3 picks. White, 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 black, white, black, white, and on down. And then finally for 4 picks. So my top one is, my outcome is in terms of I picked 4 white jelly beans and 0 black. And there are 16 outcomes for 4 picks from that jar. Each of these outcomes is mutually exclusive, meaning that there is that combination does not occur anywhere amongst the 16 picks. So if I say, this outcome here, white, 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 black, that combination does not occur anywhere else. So each combination is unique, and they're mutually exclusive. Right? There's no relationship amongst the combinations here for 4 picks. Okay, and the probabilities are 0.5, 0.5. Okay. So I can have the probability here. Let's say it's white. My little pen's not working, and I don't know why. I must, but I cannot. So the probability here is 50% or 1/2. So this is white. Let's do white. Sorry, I have to, and I can draw as well as I can print. Or 55 or 0.5. And then the probability here is 1/2. So I'm just putting it in fraction mode. Sorry, I gotta delete this guy here. I'll just leave it. I'll scratch it out. That should go right here. And there should be an arrow here. These are 4 picks. So 1/2. Sorry for my writing. And this will be the black path down here. And then 1/2. So the probability of white, 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 white is 1/2 times by 1/2, 2, times by 1/2 times by 1/2. Right? So 1/2 times by 1/2 times by 1/2 times by 1/2 is 1/2 times 1/2 is a quarter. 1/4. 1/8 is 1/16. So the probability of each outcome, because each outcome is a half times a half times a half times a half, the probability of each outcome is 1 over 16. So 1 over 16 is the probability is 0.0625. So the probability of each outcome is a half times a half times a half times a half is 1 over 16 or 0.0625. And because it's 50-50, they're of equal probability. So if I add up each of these outcomes, each of these probabilities adds up to 1. So this is an exhaustive list. No other outcome can occur. Now I have here the number of black jelly beans. So the first one's white, 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 no, 0 black. The next one is white, 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 black. If I don't care about when I pick a jelly bean, all I care about is how many black that I pick, then there's 4 possible outcomes of picking one black jelly bean. So there's where I pick it last, I pick it second last, I pick it second, or I pick it first. So for the picking of one black jelly bean, there are 4 possible outcomes. So if all I care about is if I pick one black jelly bean, I really only have I have 4 outcomes that match that criteria. So I can add those probabilities together. So if I add them together, it's 1/16 plus 1/16 plus 1/16 plus 1/16, which is 4 over 16, which is 0.25. So the probability of picking one black jelly bean is 0.25. Okay. So I can then, add up. So the probability of picking 0 black jelly beans, there's only one occurrence of that. That's white, 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 white. That's 0.0625 or 1 over 16. The probability of picking one black jelly bean, that occurs 4 times. White, 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 black, white, white, black, white, white, black, white, white, and finally black, white, white, white. So there's 4 outcomes where I pick one black jelly bean. 1 over 16 plus 1 over 16, do that 4 times, gives me 4 over 16, which is 0.25. And then if I look at the probability of 2 black jelly beans, that probability is 0.375. And the reason for that is, if I look at the probability of 2 black jelly beans, there's 1, 2, 3, 4, 5, 6 outcomes. So 6 over 16, which is equal to 0.375. So these are the outcomes here, right? 0 black jelly beans, 0.0625. 1 black jelly bean, 0.25. 2 black jelly beans occurs 6 times and a probability of 0.375. 3 black jelly beans occurs 4 times, 0.25. And then 4 black jelly beans, that occurrence only happens once, right? Black, 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 black. Okay. Now, if I'm drawing a sample, and this is kind of like the heart of inferential statistics and estimation. If I draw a sample and I get 0 black jelly beans, the probability of that occurring is, if I were to run this study 100 times, that would occur roughly 6.25 times. So out of 100 studies, 6.25 of the time, I would end up with 0 black jelly beans. The event that would be, if the true population is 50-50, what I would expect is I would end up with 2 black jelly beans and 2 white. That event, which is if the true population is, in terms of that jar of a million beans, it is truly 50-50, much less than half of the time of 100 samples, only roughly 38 of those samples would truly match what's going on in the population, right? That's my sample of, it's just random sampling from a jar, 50-50 probability of white or black. And if I pick out 4 black jelly beans, roughly 38% of the time, or 38 out of 100 studies, I would end up with 2 jelly beans. So in terms of, if you think of a study as being replication, if I were to replicate this study 100 times, and for each of those replications, I randomly picked 4 jelly beans from that jar. Of my 100 studies, only roughly 38 of those studies would match what's truly going on in the population. So then I have to make a decision. Am I in a position, if I picked 0 black jelly beans, am I in a position to say, you know what, I have enough evidence here that I don't think that there's an equal number of jelly beans in that jar. I suspect there's disproportionately more white jelly beans in that jar. Because if there truly is an equal number of jelly beans in that jar, the probability of getting 0 black jelly beans is 6.25. And then the question is, which we'll learn after study week, is, well, how exceptional does my event or my outcome have to be for me to say that no, it's not an equal number of jelly beans? And that's an arbitrary number that's just set through basically the standard within a given discipline. And what we'll see next after the study week is that magic cutoff is 0.05. If the probability of that exceptional event is less than 0.05 or is likely to occur less than 5% of the time, then I will reject the null hypothesis, which in this case is an equal number of black and white jelly beans. Now the final piece here is, if I look at the shape of this distribution, it's starting to look like a normal distribution. Okay, so this is the Quincunx, the device developed by Sir Francis Galton, and it's a peg system. So if each of this is a physical device, so you can I don't know, you can build one. So it's just a peg system. You put pegs on this board, put it on a bit of an angle, and you drop steel marbles down it. And when it hits a peg, it either goes to the left or goes to the right. 50% of the time it'll go to the left, 50% of the time it'll go to the right. So the probability of left or right is 50-50. So if I see one ball, there, bounce, 50-50. Now what I can do is I'll make it really big and I'll make it really fast and I'll restart. So here it goes. So it's dropping pretty quick. If I drop enough of these balls, as you'll see, most of them occur right in the middle, right? That's 50-50. If you think of it, going left, 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 left 15 times in a row is a highly improbable event. So we'll just watch it play out here. So what's the shape of my distribution starting to look like? It's starting to be normally distributed. And if it's normally distributed, I technically could convert these to so, and the numbers down here represent 0, 0 going to the right. So it goes to the left all of the time, 15 times. So it's 0 rights, never to the right, all the way to here where it goes 15 times to the right every time. So it'd be like the white, 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 white example from the jelly bean. So if I watch this, I can see how it'll start to form and be normally distributed. And the extreme events are highly unlikely. So the probability of it going to the right 15 times in a row so 15 times to the row, so the probability P is 0.5, and N equals, let's say, 15. So the probability of 15 is equal to the P to the power of 15, which is one big ugly number, or small ugly number. So let's put it out here, and let's make the number, make it a number, and it is a very, very, there. So the probability of 15 times to the left is 0.0, so 1, 2, 3, 4, 5. If I were to drop, if I were to drop 10,000 marbles, So 10,000 times by that probability, it would be 0.3. So to get to just 3, it's going to have to be 100,000. So if I were to drop 100, if I were to watch this thing drop for 100,000 drops, 100,000 steel alleys or steel marbles dropping, out of 100,000 drops, getting it always to go to the left 15 times in a row, the probability of that, is 0.000003, which means that out of 100,000 steel balls being dropped, 3 of those 100,000 would end up at the 0. That's a highly, highly unlikely event. Okay, and as I allow more marbles to drop, it becomes more and more normally distributed, which will take us back to the standard normal curve. And we can see even with probability, where it's a 50-50 proposition, if I have enough of events in a sense, this would be like 15 rows of pegs, which would be a sample size roughly of 15, maybe like picking 15 jelly beans from that jar. The probability of, if it's 50-50,